We've come to a new topic on light polarization. This involves EM optics, and we have to take into consideration the vector property in wave theory. This topic will be divided into 5 parts. Part 1 will describe different light polarization states, namely the linear, circular, and elliptical polarization. And Jones vectors will be introduced to represent these polarization states. Whereas in Part 2, we will discuss Jones matrices for linear polarizer, phase retarder, and the rotator. Malus's law will be described in Part 3, and we'll look into how polarized light is produced through selective absorption or dichroism and reflection from dielectric surface. Part 4 continues on production of polarized light through scattering and birefringence. The double refraction in the birefringent calcite crystal will be demonstrated in Part 5. Polarization of polychromatic light and photoelasticity, as well as how an optically active medium modifies the polarized light, will also be discussed in Part 5. Now let's start with Part 1. So what is light polarization? Firstly, let's just look at the EM wave, electromagnetic wave. We know that you have the electric field vector in this direction, magnetic field vector in this direction, and or rather here, E cross B gives you the direction of propagation using a right hand to represent. So you see that the E and the B and the K, that's the direction of propagation, they are mutually perpendicular. Hence, since we know that this relationship in terms of orientation is always the same, so it would be enough to sort of completely specify the electromagnetic wave using just the E field alone. That's why in polarization, it will be described by just the direction of the electric field, because we will know, once we know the direction of the electric field, then we will know the orientation of the magnetic field as well as the direction of propagation. Let's consider an E field of a wave that is propagating in the Z direction, and it is polarized in the X direction. Okay, X is going to the Z direction. So the B field will be written as by Maxwell equation. You will know that it will be written related to this by a factor C here, which is the speed of light, assuming that it's traveling in vacuum or in air. So just 1 over C E0, and it will be in the Y direction. And the direction of propagation, which is given by the pointing vector, would be in the Z direction. And the force on the charged particle Q that is moving with velocity V. So the force that's exerted by the EM wave can then be written using Lorentz equation, where you have charge multiplied by the electric field, and you add to it the magnetic force, which is equals to charge multiplied by the cross product of the speed that's moving with the magnetic field. So you find that over here, the direction that the force is acting is actually in the same direction as the electric field. So again, it tells us that specifying the polarization using electric field is also very suitable. And here we know that from here, you'll find that this is the electric force, and this Q multiplied by this will be the magnetic force. Now, this force will be much larger than this force because the charge, the speed of the charge, okay, is only a small fraction of the speed of light. So the force exerted by the electric field, it would be stronger. And a lot of optical applications depend very much on the nature and the manipulation of the polarization of the EM wave. That's why polarization is an important topic. Now, Let's look at ordinary light. I'm not sure whether you've seen this, but these are the incandescent bulb that I used to use in my time. Um, Here, light is produced by a number of independent atomic sources whereby the radiation given out is not synchronized. And the resulting E field vector then would then be made up of many, many components whereby the amplitude, the frequency, the polarization, the phases would all be different. So therefore, we then talk about unpolarized light, yeah? Or we can say it's randomly polarized maybe. So you'll find that the polarization of the individual fields are randomly distributed. So they are in actual fact, it is unpolarized. Yeah. So if you look at this can be one polarization, this can be another polarization, but they are all randomly distributed. But for each one of these polarization, we can extract out just one of this, and we can resolve it into a component. Let's define vertical and horizontal x, y, and x. So to the x component and y component, whereby the x component is just a cosine theta, y component is a sine theta, and the net. And what happens if we resolve every one of these possible polarization, then we can just add on the vertical one and add on the horizontal one, and in the end we can sort of represent it. A net effect of this is representing it by two orthogonal vibrations of equal amplitude, but they have no coherence in phase at all. So it's a rather oversimplified representation, and it's drawing this where the wave is coming towards us. Then in that sense, if the wave is coming from my left to right, then we will draw it using arrow phasor that looks like this, vertical and horizontal one that's going in and out of the page. That's to represent this one here. But it is an unpolarized light. There's no coherence of phase, yeah? We would like to explain about polarized light. So you can think of polarized light as the electric field vector having a fixed direction of oscillation. So in that case, we're talking about plane waves that is oscillating in a plane, like this one here. Or it can vary spatially in a regular manner, like those represented by circular and elliptical polarization, whereby you see that if you view it end on, you'll see that the resultant vector from these two superposition of these two waves, two plane waves, like EM wave, here they are out of phase by 90 degrees. You'll find that, and they're of equal amplitude, so it will then scribe out a circle. If they're of different amplitude, then you find that it will scribe out an ellipse. Now, one property which is very important is only transverse wave can be polarized. So let's start with linearly polarized, or sometimes we call them plane polarized light. So for this particular light wave, the oscillation of the electric field is in a plane as represented here. And associated with the electric field, there's also the magnetic field, which is orthogonal to it. And that magnetic field and the E field are actually in phase, but we only need to represent using the electric field. It will be enough. So if you look at it end on here at the tail end, so you'll see that the electric field is actually oscillating along this line here. Or if you draw it with that simplistic representation, if the direction of propagation is from here to here, then we can draw as vertical, so the plane is oscillating in up and down. And if the plane of oscillation is horizontal, then you can just draw the dots here, and it's propagating from here to here. And if you look at that electric field vector, how does it change with time? Just looking end on as the wave is coming towards you, you'll see that the electric field is actually starting from 0, when time is 0, assuming, then it will project along here until its maximum amplitude, then it shorten, and then it flip, go back to 0, and then it flip the other side, the positive side, and it grows in length, and it will reduce and come back to 0. So this represents a full period. So, and in this case, the example is shown for a plane polarized light wave, which is in which the plane is inclined at 45 degrees to the x-axis or horizontal axis, and the electric field vector can be represented in this way. So you have equal component in the x and the y direction. So circularly polarized light actually consists of two perpendicular EM plane waves. They are of equal amplitude, okay, same amplitude, but they have a phase difference of 90 degrees, right? So these are the important feature of the circularly polarized light, how we represent it. So here, this darkened one, dark shaded one, is a horizontal plane wave, plane EM wave, and this one represents the vertical EM wave, but we only represent the E field again, and they are out of phase by 90 degrees. So resultant is this one that moves in a circle. As you can see over here, at every point here, we get the resultant field, and you find that at every point you find that the resultant field is represented by this arrow as you view from this side. So viewing from that side, you can imagine, use your imagination, you point your right hand towards the source. Okay, point your right hand towards the source. You'll find that this tip is actually moving clockwise. So your hand here moving clockwise. So this is a right-handed circular polarization. It's moving clockwise, yeah. And here we can see the difference of left-handed and right-handed. Now, what we'd like you to see is this plane here, this black circle here. Let's look at the plane. Now, inside it, you have a thick arrow here. As this circularly polarized light passes through this fixed plane here, you see that the electric field vector is actually turning. Okay, now when you're viewing it this way, you will see that it is turning in an anti-clockwise direction. So that's left-handed circular polarization. And if you view this one instead, this arrow is actually moving in a clockwise direction. So that's right-handed circular polarization. And note the difference between circular polarization and linear polarization. So the representative component plane waves are the blue line and the green line here. They are equal amplitude, but they are out of phase by 90 degrees. Here, they are equal amplitude, but they are in phase. The two EM plane waves are in phase. So the resultant will always be this red plane. So it is inclined at a certain angle. So what results will be a linear polarized light in this case. So this is what we have explained just now. What you see would be the electric field vector will make one complete revolution as the light advances one wavelength. How do we create circularly polarized light? So what we do is we bring an unpolarized beam, let it pass through a linear polarizer, and the linear polarizer will have its transmission axis inclined at 45-degree angle, so that you can resolve one component vertical, one component horizontal when it reaches the quarter wave plate here, and they would be of equal amplitude. Okay, so but what the quarter wave plate does is, as it will introduce a phase difference between the vertical and the horizontal component plane wave as it progresses inward. So it will introduce cumulatively such that at the point of exit, the difference in phase between the two would be a quarter wave, which is equivalent to a phase of pi over 2 or 90 degrees. And being equal amplitude, they both superpose back and it produces the circularly polarized light. Now this this is the diagram that shows you as it progresses with time how would the electric field vector moves. So the ray is coming towards you and you see that this will be rotating and the edge at the tip of the arrow would then draw out a circle. So this is circularly polarized light. And as you can see, you can represent it using this expression here. Now, if you write both in sine function, it's easier to see. Then you see that the second component, the y component EM wave actually has a phase of pi over 2, whereas so the difference in the phase is pi over 2. What about elliptical polarized light? We can represent it by two perpendicular plane waves, and they are of amplitude which is not the same anymore, and they're out of phase by an angle, can be any phase angle other than n pi, as long as they are not multiples of pi. So here is shown for a phase difference of 90 degrees. So that's why, and here we have different amplitude, but phase difference 90 degrees. What we get would be an ellipse. Major axis along Z, the minor axis along Y. Okay. Again, in definition of left and right-handed elliptical polarization, it would be similar to what I show you for circular polarization. If there are many different polarization that superpose to form a certain electric EM field, and if there exists one or more that predominates, is not totally composed of one particular plane polarization, but one of the plane just dominates, then we can say that the field is partially polarized. We discuss linear polarization, circular polarization, and elliptical polarization. And that was qualitatively describing it. Now we would like to represent polarized light quantitatively using mathematical expression, which is known as Jones vector here. Basically, it is a two-element column matrix, and that will represent the state of polarization. Now, we know that the vector, electric field vector, actually vary continuously in magnitude and changes direction every half period. You've already seen that just in the previous part. Now, at a particular time, we choose a particular time t, so we freeze it and we can then represent the electric field vector by a resolved component in the x and the y direction. And if we were to write it in full, which will include the time function, then it's better that we represent it using complex form. So we will have the electric field vector in complex form with a curly hat here is to mean this complex form. And that would be represented by the x component, which is the amplitude E0x, exponential I kz minus omega t plus the phase of that component. And the y component will have a phase of phi y compared to phi x here. So basically, we can then represent this as the x complex component, and this will be the y complex component of the E field. And if you note here is kz minus omega t. So this tells us that this wave is traveling in the z direction, and it has amplitudes given by E0x and E0y. And the phases of these two waves will be phi x and phi y. So how do we relate this to this? Now, this is actually taking the real part. So what we do is Ex here will be the real part of this term. Ey will be the real part of this term. So if you look back at this expression here, we have a common factor, which is exponential ikz minus omega t, which we can factor out, as you can see over here. And remaining inside the bracket here will be E0x exponential I phi x and E0y exponential I phi y. So then we represent this term here, which is called the complex amplitude by E with a curly hat 0, and we still have the time function here. So this will describe amplitude and phase, yeah? So that would be describing, just this term here would describe the state of polarization. And if you write it in matrix form, it will result in a two-element matrix, which is called Jones vector. So that the first element is E0x exponential I phi x, and the second element would be the y component. Now, let's look at how we would represent it for linear polarization, whereby the plane of polarization is vertical with an amplitude of A. In other words, E0x is 0, E0y is A. And this is 0, so it results in 0. This amplitude is A, so we will then have 0A, and you can factor out A, and that leaves 0, 1. So this is a polarized light or EM wave that's traveling in the Z direction, and the Z direction is out of the page. What if it's for horizontally linearly polarized light? Basically, we have E0x with an amplitude, E0y has no amplitude, so that will be written as A0, factor out the A, then multiply by 1, 0. That is for horizontal and vertical and horizontal. What if is a general case whereby the plane of polarization is inclined at an angle alpha? In this case, we could resolve an x component, which is a cos alpha, and a y component, which is a sine alpha. And in this case, it's inclined in the first and third quadrant. So alpha is positive. If it were to be inclined in the negative, in the third and second and fourth quadrant, just now was first and third, now if it's second and fourth quadrant, then alpha would be negative. So we will represent then the elements by here we have a cos alpha, and the bottom one will be represented by a sine alpha. Take out the factor a, you have cos alpha and sine alpha. So you find that linearly polarized light would then require x and y component to be in phase. In other words, the relative phase between them is actually 0, or they can be out of phase, whereby the relative phase between the both of them is equal to pi, in which case the resultant vibration will be along a line with negative slope, whereby alpha is negative just now. E vector will be in the second and the fourth quadrant. And now we're going to define what we call as the normalized form of linear polarization. So if we say we have a general vector, we're given by A, B, element of A and B, such that when you square this term and square this term and sum it up is equals to 1. Well, that's possible. Just now when you have an inclined angle alpha, we have a cosine square alpha, sine square alpha. When you add that 2, you get 1. So in this case, for the normalized form, then the factor A that we took out which was here. Sorry, here. So this one we set to 1, then we will have the normalized form. So for example, Jones vector for vertically linearly polarized light, which is 0, 1. Here you see that 0 squared plus 1 squared is equals to 1. So that is already a normalized form. So we set A equals to 1. Now, given a vector represented by real numbers A and B, then if the inclined angle when be obtained from taking the arctangent of B over A, which is actually equals to arctangent of the y component over the x component. So in summarizing this, then this Jones vector in general form, whereby the element are real numbers, both of them are real numbers, this would represent linearly polarized light at inclined angle alpha given by arctangent of B over A. So now let's try out a problem. For example, if we have a wave written as with amplitude in the x direction as 8e0 and in the y direction as 6e0, and we have the time function here. So how are we going to determine the amplitude, wave direction, and the state of polarization of this particular wave here? So if we compare this to what we wrote in the complex form, well, then you see that E0x is actually equals to 8E0. E0y is actually equals to 6E0. And phi x is equals to phi y, and that is equals to 0. So here, so that is the amplitude, yeah. And the direction of the wave, well, we look at the time component, it has a z term here, so it's in the positive z direction. This is negative, so it's positive z direction. What about the state of polarization then? Then we look into Jones vector. So for the elements in Jones vector, we can just represent what's in this bracket now. So that's 8, 6. Now, if you were to factor it so that you can get the normalized form, you can divide by 10 is 0.8 and 0.6. If you square this and square this, is actually equals to 1. So this would be the normalized form. So what would then be, so it's a linearly polarized light because this real number, this real number. And what would be its inclined angle that is given by E0y over E0x, which is 6 over 8. Take the arctangent of that, that gives you 36.9 degree inclined with the x-axis. And the amplitude of this, well, that will be 8 squared plus 6 squared, and you root that. So 64 plus 36, that will be 100, root that, that's 10. So the amplitude of this wave is 10 E0, so E0. Next, we are going to work out Jones vectors for circular polarization. Well, for circular polarization, the two orthogonal EM plane waves, they have amplitude of E0x and E0y is the same, then, but they have a phase, relative phase between them, and that is a pi over 2. And let us take, for example, that EX component would lead EY. So it's leading EY. So in that case, you'll find that this resultant E field would then be moving in this direction. Let's take time equals to 0, and we say that it is at a position, horizontal position. So EX is equals to A here, positive A. Now, at a quarter period, it would have turned 90 degrees, where EY would now have an amplitude of A, and EX would be 0 amplitude. And what about in between? Time equals to 1/8 of a period. Then you find that this angle would be 45 degrees, which is pi over 4. So EY and EY would then be A sine pi over 4. EX would be A cos pi over 4. Now, looking at this illustration, you will see that basically the X vibration is actually leading the Y vibration, but phi Y is larger than phi X. This apparent contradiction actually comes about because of the way we choose to represent the wave, in which the time-dependent term actually in the exponential part is a negative. For example, let's choose the wave at z equals to 0 with phi x equals to 0, and let's take phi y. Now we say that phi y must be is larger than x for this example, is equals to epsilon. In other words, phi y will be larger than phi x. So the wave function then can be written as for the x component E0x exponential I kz minus omega t plus phi x, which is 0 here. So that leaves us with E0x exponential, because z is 0, so this term goes to 0. So exponential negative I omega t. For the y component, phi y is epsilon. So it will be exponential negative omega t. This term is 0 since you're negative outside. So we have a negative epsilon. So this negative sign before the epsilon would indicate that y actually lags the x vibration by a phase of epsilon. X vibration is leading. Okay. Now, if we take the real parts, then and we set E0x and E0y equals to 8, amplitude equals 8, and we take epsilon equals to pi over 2. These are the conditions for circular polarization. So we can then write EX as A cos omega t, and EY will be cos omega t minus phi over 2, which actually equals to A sine omega t. And we also have the resultant electric field amplitude here. Squaring that will be equals to EX squared. If you look at this diagram, E squared equals EX squared plus EY squared. So that will be equals to A squared into cos squared omega t plus sine squared omega t. That is equals to A squared. So in other words, we have the tip of the vector tracing out a circle of radius A. Now with this condition, definitely this tells us that phi y is larger than phi x. So then we can write as the amplitude, the element for this component, for the x component would just be A, and for the y component then, okay, we write the amplitude, this phi x is 0, so phi y is pi over 2, so we have A exponential I pi over 2. And what is, we factor out A, so we left with 1 and exponential I pi over 2. Now, expression I pi over 2 is actually equals to cos pi over 2 plus I sine pi over 2. Cos pi over 2, cos 90, cos 90 is 0. Sine 90 is 1, so that gives us only I. That's why we just have the term I here to represent this term here. And we want to get the normalized form. The element here squared plus this one squared must be, you have to equate it to 1. But when we do that, you'll find that that's equals to 2. So the way to get these terms to be unity is to divide each of these terms by root 2, by root of the sum here. So therefore, we can then write, because we only want the state of polarization, just look at what's inside this the vector. Then we can write in the normalized form as, so we don't have to specify a here. 1 I, we have to factor out of root over 2, so we actually divide by root 2. So this particular, because we have a phi y larger than phi x, so we then see that E is actually going to rotate in a anti-clockwise direction when we view it here. That means the wave is coming towards you. So that would give you left-handed circular polarization, because if you use your left hand to point to the source, your fingers will curl in an anti-clockwise direction. And you find that this term here has a pure imaginary expression. Just now for linear polarization, both of these must be real number. Now for circular polarization, you find that the second element is actually imaginary. What about for right circular polarization? In this case, you find that EY leads EX by pi over 2. So the resultant electric field amplitude vector would then rotate in a clockwise direction. So instead of pi over 2, we replace the pi over 2 with negative pi over 2. And then you will work out that the representation for right circular polarization would then be given by this expression. This is in normalized form. We have already normalized it by dividing by root 2. So this 1. And the second element has got a negative sign now. And it's again purely imaginary. But the actual character of the light may not immediately be clear unless we do some manipulation mathematically to get whatever is written in the bracket to be in the form that we can recognize. For example, we have 2i over 2. Bring out the 2 factor. We have I on top and 1 at the bottom. No, that's not the form that we want. We need to get I to the bottom. So then we divide by I, that's 1. That means we take out the I here. The prefactor will just affect the amplitude. In other words, it will affect the irradiance, but not the state of polarization. The state of polarization is specified only by what's in the bracket here. So, and this term here will have a negative I. So this will tell us it's a right circularly polarized light. So for circularly polarized light, to represent it by Jones vector, you'll find that one of the element is the second element here will be purely imaginary, and the magnitude of the elements must be the same. So for left CP, left circular polarized, 1 over root 2, and you have this Jones vector 1i. For right circular polarization, amplitude is the same, this normalized form, and 1, and this negative I. Okay, that finishes our lecture 18. So I hope you would be able to do what we listed here after listening to the lecture. Bye, and thank you.